Okay, so hello again. What we want to do now is we have already successfully installed DAMASK and we want to run an example case of simulations and then see its output, global and local. We will talk about that. The first thing I want to do is I want to create a new folder in my home directory. So what I want to do is I want to create simulations, this folder. And in this folder, I want to create a new folder with name of example. And in this folder, I will run all my simulations. It is important to keep your data separate and um, yeah, run simulations in specific folders because otherwise your file will mix and it will be a mess. I want to go back in my home directory. What I want to do is I want to go in software, DAMASK, and I already want to go in this example format, spectral method, polycrystal, and in this sequence of folders there are already some files given with DAMASK that that are given with it to run some examples, and I will be using them. Okay, so in this folder you will see several files. If you will look at the online documentation, they talk about these files and they use these files in some of these examples I will be using directly from here. So I am using a 20 grain 16 by 16 by 16 geometry, a small file, or let's take a relatively bigger one, a 20 grain 32 by 32 by 32 geometry. I am selecting this. I am selecting this tension x load file. So tension in x direction dot load file, and then I am selecting this material.config file. We at least need these three files to run the simulations. I will copy them and I will paste them in my simulations examples folder here. Okay, now what I want to do is I want to run simulation on this. So instead of writing this very long name of this geometry file, I just want to change it to uh, small gem. So this is my geometry file. Okay, and instead of writing tension x, I just want to replace it with dx. So tension in x direction load. And material configuration file always have to have this material.config name with it. Okay, what I will do is I will open terminal in this folder, right? So my terminal is open in simulation example in this folder, and what I will do is I want to run simulation on that. So what I will do is I will write DAMASK spectral, and to run a simulation I have to use the switch of load file, and then I have to write this name of load file, and then I have to use the switch of geometry, and then I have to write name of my geometry file. Okay, and if I do this and I run the case, you will see that the simulation will run and it will start processing. What it does is that you will see that I have wait, here. So in my load file I have total of 100 increments, and here the simulation was run in increment number 5, and it it's at the end its error in divergence was 21.59, and error in stress boundary condition was 1.19, and there is a threshold. This error divergence has to be less than, I think, 1, and then the simulations converge. And as soon as it does, increment 5 will converge and the simulation will jump to increment number 6, and that is how the simulations are running. Let's see the progress. So increment 12 has converged, now increment 13 has converged. Um, and this simulation is primarily running on the default geometry file, material file, and load file that we just copied from the DAMASK folder, pasted it here, and started running the simulation. While this is running, let's see what was in these files. Okay, so let's look at this load file. It has um, two load steps. One in which we have defined a load in a tensile load in x direction with this deformation gradient for time 10, and the number of increments are 40 and frequency is 4, which means it will write the output after every 4 increments in the output file. And then we have another load step which is the same in the first step. The only difference is now it is running for time 60 with total 60 increments, so every increment for 1 second, and frequency is not defined, which means it will store the output for every running increment there will be. Okay, so this is what is mentioned in the load file. Let's look at the geometry file. So from from the initial file name, we came to know that it is a 32 by 32 by 32 grid size with 20 microstructures, so 20 grains. And for example, we can see here how the grains are distributed. So we see grain number 2 here, grain number 4 here, grain number 8 here, 13 is here, right? And then 10 and 2 and 4, and this is how basically our microstructure is divided. These are just the numbers. We talked about what they define in the previous video, but you get the idea that all the addresses of every 32 by 32 by 32 solution points is given here, and based on these points we have information in our material configuration file. So what you will see here is that they have defined um, a simple homogenization scheme um, with almost all the outputs here, and the phase is aluminum phenomenological power law, and in this law they have used Hooke's elasticity and phenomenological law plasticity. They have exported some um, um, possible outputs here, and then for example we will see that the lattice structure is face-centered cubic, number of systems are 12, number of twin systems are 0, then there are elastic phases given, and then there is initial shear rate of slip, and number of slip systems are 20, um, initial tau slip, and then tau saturation slip, and then a coefficient of the hardening coefficient of the slip system. This is the hardening coefficient, and then the interaction of slip hardening matrix, and then the coefficient of hardening law. So you can know what these parameters are and what do they do from the phenomenological model that they have published in their research papers before. Is there something mentioned? No. And then this is the information about the microstructure given. Probably this file will be bigger than, no, it has 20 grain information about 20 grains, and then texture information about 20 grains, and that is how this file is written because we only have 20 grains. Okay, so this is what was written in these three files, and our simulation is still running. Increment, I saw that increment 87 has converged. Let it run for some time and then we will start with processing. So increment 91 has converged. Okay, so what we see is that 100 out of 100 increments have converged, and the results have been written in the folder. If we look at the folder, we started with only three files: material configuration file, geometry file, and load file. And now we have all these new files that have appeared here, right? And this is the spectral out file in which all the output data is written. We will see how to read that later. Um, but we have this STA file, the status file, which tells us for which increment, what was the time step, and how many iterations, and the number of iterations that were needed to converge, and did it converge or not, right? So true or false. And what we see is that all the increments converged. There were no cutbacks. Um, Usually 3 or 4 iterations were necessary to converge them, and in the end we completed all the steps. Okay, so far so good. What we want to do is we want to look at the data in the spectral out file. Now there are two ways of looking at data. One is by processing data to look at the average data for every increment in terms of a global stress strain curve, or the other way is to look at data um, as to look at data at a specific increment which is local, so on every element or phase. And talk about we will talk about this. um, First, if I want to extract data from um, the the spectral out file, there is already this this pre-written script with Python, and pre-written script with DAMASK. And if DAMASK is installed, I should be able to call this command on post results, right? And then we are talking about the crystalline results, the deformation gradient, stress gradient, and what I want to do is I want to write the name of the spectral out file. So the name of my geometry file was small, yeah, and spectral out file, right? So this is the name of my spectral out file in the folder. If you do not know that, what I will do is I will just run ls here, and this is my spectral out file here. This is the name. So what I can also do is I can just write post results crfp, and just copy and paste this. Yeah, right. If I will do that, what it does is it tries to average out all the 9 components of deformation gradient, and deformation tensor, and the stress tensor, and then it writes them in the it writes them in the a text file, which we will be able to see after it is finished. While this is happening, what I want to do is I want to install ParaView. Which ParaView do I have here? I have ParaView 5.9. So what I just want to do is I want to go to 5.9 or 5.7. Just voice one. Okay, we are downloading it, and this has finished. Okay, so how do I see this output? One way of looking at it is um, um, I will have a new folder here, post proc, and this is where all the output is now written. If I go in this folder, I will have this file small underscore tx.txt. I can try to open this file and I see all this data, right? If I just want to see its header, what I can do is um, show table help show table dash a and then this file name, and it will show me the the header of this file, right? And what I want to do now is I have nine components of deformation tensor, nine components of Piola-Kirchhoff stress tensor, and what I want to do is instead of working on nine components, um, I want to first convert them into um, Cauchy stresses and Mises strain, right? So first what I will do is I am in this folder, and what I do is I do add Cauchy stresses, add Cauchy, um, and I write the name of this file. It will add all the Cauchy stresses corresponding to the Piola-Kirchhoff stress tensor here, and then I write add strain tensor. Dash 0 means log 10, dash v means logarithmic, and then I enter the name of my file, and now I've added the 10 log strain tensor, natural log strain tensor of um, the deformation gradient. Now if I look at this header, right, it will look like this, right? So previously it was just these nine components of deformation tensor, nine components of stress tensor. Now I have these, right? Nine components of deformation tensor, nine components of stress tensor, and on top of that, I have nine Cauchy stress components and nine logarithmic strain components in my file, which were calculated from them. What I want to do now is instead of dealing with these tensors, I want to convert them into equivalent Mises stress and strain. And there's already script available with DAMASK which we can use, which converts them into this. And what I have to do is I have to say add Mises stress and then name my header, which is this Cauchy, and then I have to write the name of my file. Okay, and similarly, if I want to add Mises strain, what I have to do is write here Mises strain, and instead of writing Cauchy, now I have to write here this header. The only challenge is because it has special characters, so that is why I'm enveloping it in the commas. I run this, and it has this, and they're added. What I can do is I can see my table again, and now, for example, you will see um, two more lines of text added: Mises Cauchy and Mises strain. Right? Um, what we can do is we can clean up this file. So instead of just going through all these texts, we can only have these two in our file. So what we do is we want to copy this as clean, and now um, filter table whitelist of this file can come at the end, but with the whitelist in which we want to add increment and what I will do is I will just write it here because it has special characters. Mises Cauchy, and then Mises strain, okay, and I want to run this function on this new file that I've copied. If I will run this, it will filter the table. It will say, okay, the command is successful. And now if I see the header of this file, so you will see that I only have this text here. If I open it with a simple text editor, you will see that I have this data in, which is basically the Mises strain, right? And the Mises stress. What we can also do is we can apply functions on them, and we can divide this, for example, with 10e6 to convert it into, this is for now in pascals, we can convert it into megapascals. This for now is in real values, we can convert it into a percentage by multiplying it with 100. The formula to do that will be add calculation, and then we want to give it a label, Mises stress MPA, and then the formula is, in the formula I have to write this as bar, I have to add hash to show that this is a variable which I want to, or separate different mathematical entities, and 1e6. So I'm basically dividing it by 1e6 in file this. The calculation is added. I will add another calculation. Mises strain percent. The formula is, let me clear this, let me copy this, yeah, and multiply it by 100, and running on the same file. Now I have this. Now if I look at the table header, I have these two more terms here, right? And if I open up this file, I should have the same value of stress converted into megapascal and same value of strain converted into percentage. Okay, so you see here that I'm starting from 10 to the power minus 12, it is 65 megapascals at one point, and then I am reaching 86 megapascals, and similarly for 6.7% of 6.7% of strain value. Okay, so this is and for example, if I open up this data, can I open with other application, view all applications? No. I should have Libre. No, I don't have it. But the idea basically here is that I will be able to plot them on a stress strain curve, and it will just be um, for example, a stress strain curve. If you plot this, the problem here is that these are all the averaged values, right? One of the big advantages of running crystal plasticity simulations is that we can see how the individual grains were deforming, what was the local stress state, and what was the local slip mechanism or the hardening mechanism and things like this. But these are just the average stress and strain values out of them. If we want to look at the local behavior of the material, what we want to do is we want to look at a local frame of all the elements and not the averaged values, right? For that, what we want to do is we want to process the spectral out file, the binary file, a little bit differently. Instead of averaging out all the values for all the increments, we want to specify an increment and look at the results at that increment. Okay, so for example, from this file, I want to look at the results at this very last increment, right? The increment number you can see is 97, right? At this increment, I have the maximum strain of 6.5% with stress of 86.29, average stress of 86.29. So if I want to look at my results here, what I will have to do is I go here, and previously we ran this command. Yeah. So previously we ran this command: post results cr crystalline fp and then on this spectral out file, which becomes slightly different if we want to extract the results on a specific frame. So what we do is we say cr fp, and what else do we want to get out? Let's say phase, um, Euler angles, um, and texture. So all of this should already be exported. Otherwise, we will not be able to look into this. How do we do that? We go here, we look at this material config file. So you will see here that in the crystalline, we have all these um, um, values that are written as an output. So phase, texture, volume, orientation, Euler angles, and things like this. And from here, we are exporting F, P, phase, texture, Euler angles. Okay, so this is what we are writing here. From crystalline, export FP, phase, Euler angle, texture. And what we want to do is we want to separate the results. Separation X, Y, Z. Then split range 97, 97, 1. So this is my frame which I want to extract. If I want to extract, for example, frames from 50 to 97, I will write here 50, 97, and then maybe with one step or with 5 steps. But for example, here I only want to extract one frame, so I'm just writing the range is 97, 97, 1. And then I give increments, and then I want to write the name of the file. I am in the wrong folder. I will not be able to run this command, but star.spectral out. If I will run this command, it will give me an error, right? I know this because I'm in the wrong folder. I do not have my spectral out file here. But if I run this command here, I either star.spectral out, because I only have this one spectral out file, it will automatically detect it. Or if I write here this, what it will do is now it will extract all these results on this increment number 97. If I go in my postproc folder, I will have now this file, which is small text for specific increment 97. I have this text file. If I try to look into it, it will have data for all the 32 by 32 by 32 solution points, right? So no. Mm-hmm. Okay, so for the last increment, for every element, it has all those 9 components written here. So the file is quite humongous. How do we make sense of it? What we want to do is we want to run the same functions on it, right? So what we want to do is we want to add Cauchy, and the name of this file, increment. It will add all the Cauchy strains. the file is not so small, so it will take a little bit time. And then we again want to add strain tensor 0v and run it. It will again take some time and try to add the strain tensor to it. And then what we can do is we can write add mesos strain log of, oh, where did it go? Log of v and this file, and then add mesos stress Cauchy, the same file, and once this is done, what we want to do is we want to create a rectilinear grid on which then we can write rectilinear VDK rectilinear grid, and we want to create that for our this file. It is created. Now if I look at the file, we have this rectilinear grid file. VTR, I will just select this so I can always paste this name. And now what we want to do is we want to write data from the text file on this empty grid that we can then visualize later. VDK rectilinear and rectilinear grid data in place data and what we want to do is we want to write the things that we need here. So lm node node is not necessary. Grain phase texture we don't want to write Euler angles here now because we will not really be using them. The important thing is we write the mesos Cauchy and mesos log of v vdk, and we write the name of the vdk file, which is this one, and then we write the name of the data file from which we want to copy this data. If we will do that, then this data is written in the VDR file, which is this one. And the question is, how do we visualize it? ParaView is downloaded. We we read this data using ParaView. What I will do is I will cut it. I will move it to. I will move it to Home Software here. I will extract it here. It will take some time because a big file. Yeah, and then I go here in bin, and hopefully I'm able to run ParaView. Am I? Yeah, it runs. So this is the outlook of ParaView, in which we can read these files. But just for a quick overview, I want to go back to my folder where I had this file. I have this file here, right? So there are multiple ways of opening it in ParaView. One way is just drag and drop. The other way is I can open a file in ParaView. I will just try to drag and drop it here. Okay, so the file is here. I can see this. So I have this cubic box because it is 32 by 32 by 32, equal in all sides. I want to see the surface, right? And then, for example, I can see my phases, right? It only has one color because it is just one phase, right? We can see textures, and this is where we will start seeing different grains, right? So this is one grain, another grain, another grain, another grain, right? So all these grains have different orientations. We did not export Euler angles, or we did not export it well, so we cannot um, see the exact orientations here. But all these grains basically have different orientations. They only have single phase but different orientations. And then, for example, the interesting thing is we can see the local strain distribution. Okay, so this is the local strain distribution, and what we see here is that in this grain the strain is much less as compared to this grain in which it is quite high, right? So um, 2.5, so 25% strain is, or 20% strain is present here, whereas here we only have almost 5% strain, right? And then where the strain is less, right, which means this grain has a more favorable orientation, which has less favorable orientation to deform, therefore it has less strain, so theoretically it should have higher stress value, and we see that the stress in this grain is higher, and the stress in the other grains which have already deformed significantly is much lower. And for example, we will see here that on the grain boundaries where there are two grains combining, the stress here is significantly higher. We can interpret all these values, we can look at it in more detail, we can plot all the histograms, and we can do all this um, for different cases. But basically this is a very basic simple example, um, starting from the default given libraries or files, to run a simulation, to extract its results from a binary file, to average them, or look at the overall average stress strain behavior of the material, or for example on a specific increment, um, look at the local distribution of stresses or strains. We can also look at the local distribution of several other things. I have not exported them in this file right now, but we can do that as well. One thing that I want to mention here is that Currently, I did everything. Um, I did everything by writing commands manually, right? But this is a very repetitive task. Usually, we always have to repeat the same set of commands. So what I have done in the past is I have tried to create scripts that run the simulation automatically, that post process the results automatically, and that can and that save the files that I can quickly look into. So I do not have to type all these commands myself again and again and again. If you want to look at the examples there, what you can do is you can again go to my GitHub um, repository, and if you will click on Damask, what you will do is you will be able to see these kind of SSH scripts, which are shell scripts, which you can run in Linux. And what they do is, for example, if you are in a certain folder, you have placed this, it will set the maximum number of threads to a certain value, and then it will then basically it will identify which geometry file you have, which load file you have, and it will run this um, 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 it will run this um, simulation of DAMASK. Once the simulation is complete, it will automatically post-process the results and will write them down in the output file, which I can then later see. Or it will ask me in the beginning from which increment to which increment do you want to post-process the results, and once it has written down the global files, it will start writing the output results for every local increment that I expect, right? And then in the end, everything will be finished, and once the simulation is finished, processing is automatically finished. I can look at the files and then I can see what I want to do with them. So you can get inspiration from this. You can, once you know that this is how you post process your files, you can write your own scripts so that you can just automate the process. And for DAMASK 2.0.2, some of the key files that I use for some of the materials, you will see that there are different versions of them. You always have to be careful with what is written in the commands and which one are you using. But yeah, um, um, there are different versions of them, and you can see which one to use. Which one do you want to use and want to modify for your own case and study. So yeah, that was all about running an initial example with DAMASK 2.0.2, and in the future we want to run more complicated examples and see the effect of different um, input variables on the outputs and how we can post-process the results in a meaningful way to get useful plots and graphs so we can know more about the material deformation behavior in detail. Okay, so thank you so much and bye.